Welcome back to the deep dive, everybody. Today we're diving into something that, on the surface, seems pretty basic. Math talk. Getting students talking about math, right? Seems simple enough, but we're going to explore how these discussions about math can actually lead to some pretty deep understanding, especially when we start to think about the cognitive science behind learning.
Yeah, exactly. You might think, okay, getting kids to chat about a problem, no big deal. But then, when you dig into the cognitive science of it all, how are kids actually processing all this stuff, orchestrating these discussions so that they're really effective? Well, that requires paying attention to how students think.
Exactly. So today our mission is to really grasp what's going on in students' minds during these math discussions, right? Like what's happening up there. And we want to pinpoint the teaching approaches that can turn these conversations into really powerful learning moments, ultimately helping both teachers and students get more out of solving problems together in math.
Right, and to kind of help us unpack all of this, we're going to focus on some pretty fascinating work by Richland and our colleagues from their 2017 paper, Supporting Mathematical Discussions, the Roles of Comparison and Cognitive Load. So we're going to get into all of that.
Okay, let's jump right in. One of the things the paper highlights is that when students compare different ways of tackling the same math problem, different solutions, different strategies, it can be this aha moment, a turning point. It can clear up those little misunderstandings and really help them build a solid conceptual understanding of how mathematical algorithms actually work.
That's right. And I think what's really interesting here is that it's not just about like seeing different answers,
Mm,
right? It's about digging into the structure of each solution and then comparing those structures. And that requires a significant amount of thinking, of cognitive effort on the part
yeah.
of the student.
It does, yeah. And the paper gives a really cool example from a teacher named Mr. Silas. He gave his students a pretty simple problem, actually, 1 plus 13 equals. And his goal, I thought, was really insightful. He wanted students to connect the standard algorithm, like, invert and multiply if you're working with fractions, with some other ways of thinking about it, more intuitive strategies, right?
Yeah, like thinking about common denominators, using visuals to help see the relationships. So things like wholes and thirds, or even thinking about division in a couple of ways. How many parts do you have? Or how many times does one quantity fit into another?
Right. Exactly. So the goal wasn't just to get the right answer. It was really about students understanding why that rule,
Yeah.
invert and multiply, why does it actually work? And connecting that to bigger ideas like how we think about dividing whole numbers versus fractions. And of course, strengthening those math practices that are so important, like the ones outlined in the Common Core State Standards. Those math practices that are about reasoning and problem solving, not just the procedures.
Right, and that kind of brings us to this central idea of the paper, which is focusing on the mental effort involved in comparing all these different representations of the same mathematical idea.
Mhm.
So it's not just about how hard the math is in general, it's specifically about this thing called relational reasoning. And that is, as you can imagine, really important, but also very demanding for students.
Relational reasoning. Okay, so that's the core skill we're talking about here. Can you unpack that a little bit more? Like, what does that actually mean in this context?
Yeah, totally. So in the context of these discussions we're talking about, cognitive demand refers to the mental resources that, things like working memory, executive function, that students need to really flex, to really use in order to gain those deep insights from comparing different solutions. And this is a bit of a different way to think about how hard a task is for the brain than just saying a problem is easy or hard based on, the steps involved.
Okay, so it's not just about how hard the math is, it's about the brain power needed to compare those different ways of thinking about the problem. And that's where cognitive load comes in.
Exactly. The paper argues that the amount of cognitive load these discussions place on students can really make a difference in how well they learn. And if it's too high, it can actually get in the way of those important comparisons they need to make. So understanding cognitive load is super important, whether you're designing a lesson or just thinking about how kids are participating in a discussion.
Makes sense. If their brains are just on overdrive trying to keep track of different solutions, they don't have much space left to compare and contrast them, right? So let's break this down. What are the actual steps involved in really digging deep and comparing these solutions?
Well, to outline that, the paper pulls from some work by Holyoake and other researchers. The first step is understanding each representation not just as a final answer, but as a system of, interconnected ideas. So when a student's explaining how they solve the problem, the other students in the class need to be actively building this mental model of how each step relates to the others.
So it's not just passively listening, it's actively trying to understand the logic behind each approach, right?
Right. And then the second step is aligning these different systems and mapping out the key connections. So now students are doing the mental work to see, okay, how are the same parts of the problem handled differently in each solution? It's about finding those common threads, those parallels that run through different approaches.
Like seeing how dividing a whole into thirds is there in the fraction 13 and also in a picture where they've, drawn out the whole and divided it into three parts.
Exactly. And then the third step, which is really important, is to intentionally ignore any surface level similarities or differences. So, maybe one student wrote their steps horizontally and another one wrote them vertically. Those kinds of superficial differences shouldn't distract from the math.
Mhm.
Sounds harder than it seems, right? It's
Yeah.
easy to get caught up in those little details.
Yeah, it is. And then finally, after all that mental mapping and noticing, the last step is drawing inferences about the big mathematical principles at play. So, for example, understanding the relationship between multiplying by the reciprocal and dividing by a fraction.
Right. So as you can see, it's this complex, multi-layered process. And the paper points out that, students might participate in discussions without really doing this deeper level of comparison. They might be talking about strategies, but not actually grappling with the similarities and differences, in a way that's going to lead to learning.
And I think that's a key insight for teachers too, right? Because as the expert in the room, they already have a deeper understanding of the math. They might not realize how much guidance students need to actually go through this whole comparison process. They might assume it's obvious, but it's not always obvious for the learner.
Exactly. And this brings us back to those crucial cognitive resources:
Mhm.
working memory and executive function. These are essential for this whole process to work.
Right. So working memory is our ability to hold information in our minds and work with it in the short term, right? So if a student is explaining their solution out loud, everybody else in the room has to be holding that information in their working memory just to follow along, let alone analyze it. It's a lot to juggle.
It is. An executive function is like the brain's control center. It manages what information gets into working memory, helps us switch between different tasks, ignore distractions, and update our thinking as we learn new things. So, if a student starts to explain something and then, oh, wait, I made a mistake, and corrects themselves, everybody listening has to use their executive function to kind of shift gears and focus on the updated version.
Yeah, makes sense. And we all know that working memory and executive function are limited resources, right? We only have so much of that brain power to go around. So if students are dealing with a high cognitive load, they're less likely to do that relational comparison we've been talking about, less likely to do it well anyway.
That's right. So some potential downsides. Well, they might make errors. They might get overwhelmed by all the information or distracted by things that aren't really important. Or even worse, they might not connect the dots between solutions at all. And so, what does this look like in the classroom? A student might memorize a strategy without really understanding why it works, or they might even cling to an incorrect idea because they just don't have the mental resources to compare it effectively with the right solution.
And so this idea of how relational reasoning develops is also important, right? The paper talks about this relational shift. What does that mean?
Yeah, so the relational shift describes how children, as they grow and learn, start to move away from comparing things based just on how they look, their surface level features, and move towards comparing things based on the relationships between them, which are more abstract and harder to grasp at first.
Right. And the paper gives that great example. I love this one, the loaf of bread and the slice of bread. They say, okay, now compare that to a lemon. And younger kids will say, oh, yellow football because of the color and shape. But older kids will get it. They'll say, a slice of lemon. And that bread and lemon thing, it really makes you realize how easy it is to get caught up in superficial similarities, even when we think we're being smart.
Exactly. And the point here is that even adults who are new to something tend to focus on those surface appearances rather than the deeper relationships that are more important. So in math class, students who don't have a lot of background knowledge are going to be more likely to miss those connections between solution methods.
Right. And it's not just about age, it's also about working memory and executive function. Kids who have stronger skills in those areas, they're better able to focus on those relationships, even when there are all sorts of distracting similarities on the surface.
Yeah, and research shows that early executive function skills can actually predict how much a student's reasoning abilities will improve over time. So this really highlights that teachers need to be sensitive to the different support needs of their students when it comes to making comparisons. Some kids are going to need more scaffolding than others.
Okay, so we've talked about why these kinds of math discussions can be so powerful for learning, but also why they can be really challenging for students mentally. Now let's get to the practical stuff. What are some things teachers can do to actually help students make those comparisons and reduce the cognitive load? The paper has some really interesting ideas.
It does. One key area is how teachers sequence their instruction and how they choose the examples or solutions that students will be comparing. So it's about planning ahead, being deliberate about what they're presenting to students.
Right. The paper mentions a meta-analysis, where they look at lots of studies together. And they found that comparing different ways to solve a problem before being taught a specific rule can actually be more effective. More effective for understanding and being able to use that rule later on. That's kind of counterintuitive, isn't it? I mean, you'd think you'd teach the rule first.
You would. But the thinking is that by grappling with different approaches first, students build their own understanding instead of just memorizing a rule. But of course, they need some background knowledge to even make those comparisons, so you don't want to throw them into a situation where they're totally
That's a
lost.
balancing act, right? Give them some freedom to explore, but make sure they have a solid foundation. And the teacher's role in selecting the right solutions to compare seems really important here.
It is. The teacher needs to be really strategic, right? They need to think about their goals for the discussion.
Hmm.
Are they trying to highlight a particular efficient method? Or are they trying to address a mistake that students are making? Do they want to showcase a bunch of different correct approaches to really get kids thinking flexibly? The paper even talks about comparing efficient and inefficient methods, which can be really eye-opening.
Right. And it all comes back to that deep knowledge of the math and how students think about it, right?
Right.
Pedagogical content knowledge. Being able to solve the problem yourself isn't enough. You have to anticipate how your students might approach it, where they might get stuck. And they gave that really interesting example about U.S. teachers and dividing fractions. A lot of teachers could get the right answer, but they couldn't explain why the invert and multiply rule works.
Right. And the paper suggests that teachers can really benefit from resources that offer some guidance on this, like which examples to use, in what order, to really maximize learning. Things like connecting with other teachers, professional development, even textbooks that include common student errors and different strategies. The paper mentions that Japanese textbooks have historically been pretty good at this, so there are models out there.
And there are curriculums that do this already, like everyday mathematics or cognitively guided instruction. They're already built around this idea of looking at multiple solution methods, so that's really promising. They talked about this idea of productive comparisons, intentionally designing those into the curriculum, which is interesting.
Yeah, that is. And then another big challenge, of course, is how to deal with misconceptions. That example from Ball's work about students adding 16 plus 16 and getting different answers depending on whether they're using manipulatives or just the symbols. I mean, that shows just how tricky this can be. It's like they're operating with different mental models of the same idea.
Yeah. And the paper makes it clear that just pointing out a misconception isn't enough. You have to guide students to understand why they might be thinking that way and show them why it's not accurate.
Exactly. And research suggests a few things that can help. So if students have some prior knowledge, if the teacher gives clear cues about the misconception, if they can see the correct and incorrect approaches side by side, and of course, if they have enough working memory and executive function to actually process everything.
Right. And they bring up this point about prior knowledge and learning from mistakes, which I thought was interesting. Some studies have found that only students with a good understanding benefit from seeing incorrect examples. But other studies have found the opposite, that the students who are struggling actually benefit the most. So how do we make sense of that?
Well, it seems like the key is how explicitly those misconceptions are addressed. When teachers are really clear about the differences between the correct and incorrect approach, it seems to help everyone. And maybe especially the students who have less prior knowledge, because they're getting more direct guidance on what to focus on.
So it's about giving them those clear signposts to guide their thinking. And that leads to the next practical suggestion, which is to provide explicit cues to compare, not just when you're looking at mistakes.
Right, that's super important. Research shows that students often don't even realize they're supposed to be comparing the things they're seeing. A teacher might plan out this beautiful sequence of examples, but the students just see them as separate things, not as things to be compared. And that can make it hard to apply what they've learned to new problems, right?
So just saying compare these two solutions is probably not enough. They need more support, more scaffolding to really pay attention to those relationships, to figure out how they're similar and different, and to draw meaningful conclusions.
Yeah, and one strategy the paper talks about is organizing solutions into smaller steps, sub-goals, instead of just this big long sequence. That can help students see the structure more clearly and make connections. And then labeling those sub-goals in the same way across different solutions, that can really help too. It helps them transfer their knowledge.
So the power of labeling is really important here. If you call the same step by the same name, it implicitly invites them to compare, right?
It does. And using familiar labels can really help students recognize that underlying structure. It makes those comparisons easier to do.
Okay, another practical suggestion from the paper is to make those representations visible at the same time. So instead of showing one solution, erasing it, then showing another, try to keep them up there during the discussion so students can see them all.
Yeah, and the research really supports this. Having the problem and the different solutions visible at the same time makes it easier to compare them directly because students don't have to hold everything in their working memory. And that can really help them learn and remember the information. It's been shown to help kids of different ages, too, and in different areas of math. I remember as a student, I used to get so frustrated when the teacher would erase things. I was like, wait, I'm not done thinking about that yet. And it makes sense now why that was such a barrier.
And that idea of simultaneous visibility is especially important when you're comparing a common mistake with the correct solution.
Right. They talked about a study where students actually learned the least when they saw the misconception first and then the correct one. It's like seeing the mistake first made it stronger in their minds somehow.
Right, because they have to work harder to overcome it. Puts more strain on their executive function. But when both are visible at the same time, it reduces the load on their working memory, and they can really compare and contrast. That's a really important insight. And the papers also talks about spatial organization, so how you arrange things visually can actually make a difference.
It does. It's about using the visual space strategically.
Hmm.
If you can arrange things so that the alignments between solutions are really clear, it helps students focus on what's important, like putting corresponding steps right next to each other or using similar spacing. It reduces the amount of work their brains have to do to figure out what to compare, and that makes it much easier to see the patterns and make those connections.
So it's about setting up the visual environment so that it supports the thinking process, like actually putting the solutions side by side so they're lined up.
Right. And then finally, the paper talks about linking gestures, those hand movements that teachers use to connect the different representations.
Yeah, those gestures can really help make those connections explicit and concrete. They can highlight alignments between steps or just show how the different representations relate to each other. And research has actually shown that when teachers use these kinds of gestures, students tend to learn more math.
Exactly. It's like the gestures making the connection physical, and that can really strengthen the mental connection as well. Teacher gesture in general is just a powerful tool, and linking gestures are a great way to specifically support relational reasoning during math discussions.
So to wrap up, it's clear that these math discussions, where students are comparing different ways of solving problems, are so powerful for building deep understanding. But as educators, we need to be really aware of the cognitive demands we're placing on our students, right?
Absolutely. That's the takeaway. We need to help them make those comparisons, and we can do that by being thoughtful about the way we teach. So planning the sequence of instruction carefully, selecting the right examples, explicitly addressing those common misconceptions, giving clear cues for comparison, making sure everything is visible, using spatial organization strategically, and even using those linking gestures.
It's about creating a learning environment that supports those mental processes so students can focus on comparing and connecting ideas instead of feeling overloaded.
Exactly. And I think this brings up an interesting question for our listeners to think about. How could these cognitive principles, understanding cognitive load, understanding how our brains compare information, how could those be helpful in other learning situations, not just in math? What if we intentionally use these strategies in other subjects? Could it lead to deeper understanding for everyone? That might be something worth exploring in the research on relational reasoning.
So much to think about. Thanks for listening, and we'll see you next time on The Deep Dive.